The universe is being pulled towards something. The galaxies are sliding, all of them, like iron filings tugged across a table, only the magnets buried under our own Milky Way. We can't look straight at it. Dust and gas in our galactic plane turn the sky into a blackout curtain, and behind that curtain something is pulling us at hundreds of kilometers per second. Telescopes argue. Maps don't agree with the motion. The names we gave the sky don't match the forces underneath. So we start with a chase. Find the pull, weigh the push from a vast void, test the rumors, redraw our home, and see where we're really headed. The pull we couldn't name, Great Attractor, emerges. Start with a number that won't sit still. The cosmic microwave background has a hot side and a cold side, our dipole. Subtract the expanding universe, and what's left says the local group is moving at roughly 600 kilometers per second toward somewhere in the constellations of Centaurus and Norma. That's not a drift. That's a decision written in velocity. Astronomers tried to point at the culprit, but the line of sight ran through the Milky Way's worst neighborhood, the Zone of Avoidance, thick lanes of dust and gas that blot out galaxies in visible light. For decades, the most suspicious part of the sky was the part we literally couldn't see. So people did what they do when a road is closed. They found another way around. Radio waves at 21 centimeters slip through dust. Near-infrared light punches harder than optical. X-rays ignore the smog and light up the hot gas in galaxy clusters. Piece by piece, a pattern bled through the fog. Get this? When the static cleared, a heavyweight stepped forward. The Norma cluster, also called Abel 3627, massive and hot, hiding near the galactic plane. Around it, walls of galaxies, Centaurus structures stretched like beams in a scaffold. The community gave the collection a name that sounded like a destination, the Great Attractor. It felt right. It explained the arrow on our velocity vector. It explained the weirdness in galaxy counts pointing that way. It gave journalists a headline. But the numbers wouldn't settle because flows hinted at something deeper downstream. Here's where it gets tricky. How do you weigh something you can barely see? You infer distances. You stack different distance ladders, Tully, Fisher for spirals, surface brightness fluctuations for ellipticals, type Ia supernovae when you're lucky. Then you compare the redshift velocity to the distance to peel away the Hubble expansion and expose the peculiar motion underneath. Every rung comes with biases, Malmquist, selection, extinction, and if you're off by a few percent, your flow field tilts in the wrong direction. Teams fought over footnotes. Calibrations weren't just technicalities, they were compass needles. Meanwhile, more of the map came into focus. The Vela Supercluster peeked out from behind the dust. The Centaurus wall traced a path that didn't stop at Norma. The attractor started to look less like a single monster and more like a confluence of structures stacked along our line of sight, strung on filaments, layered behind the Zone of Avoidance. Was the Great Attractor a place or a mirage made from overlapping walls? Then a larger shadow entered the conversation. The Shapley Supercluster, SCL 124, deeper, richer. Farther downstream on the order of 650 million light-years, Z approximately 0.046. Redshift surveys counted clusters, X-rays measured their heat, and weak lensing began to feel the dark matter scaffolding. If Shapley was that heavy, maybe the Great Attractor was just midstream, a rapid on the way to a waterfall. This was the moment everything changed. Flow reconstructions grew more sophisticated. Instead of piling up galaxy counts, astronomers rebuilt the velocity field itself, using thousands of peculiar velocity measurements to infer where matter had to be. Think of it like mapping the shape of a riverbed by watching the ripples and eddies on the surface. Where the water converges, you've got a valley and a tractor. Where the water diverges, you're sitting on a hill, a repeller. Coherent streamlines started to run past the Great Attractor's basin and bend toward Shapley's deeper well. The destination name didn't fit anymore. The Great Attractor looked like a saddle point, flat-bottomed in places, yes, but not the deepest drop. Unknown to most viewers of those first maps, a second piece was forming off-stage. The numbers hinted our motion wasn't only about pull. There was a missing part of the speed budget. Something else had to be shaping our path, something we weren't counting because we weren't looking for it. Meanwhile, back at the Zone of Avoidance, radio astronomers were still finding galaxies where star counts said there shouldn't be any. Each detection tightened the picture. Each extinction correction shaved error bars. You could feel the community moving from myth to measurement. A micro-story from that era. An observing run aimed through the plane, the spectrum smeared with foreground hydrogen. The astronomer holds the printout under a lamp in the hallway. One narrow 21-centimeter spike stands above the noise, a galaxy hiding behind the brightest part of our sky. Someone laughs, not because it's funny, but because the universe left a breadcrumb right where the map said, "Here be dragons." By the late 2000s, the lore had shifted. The Great Attractor remained in the lexicon, but it wasn't an answer. It was a clue. Our CMB dipole still pointed roughly that way, but the physics asked for scale and context. You needed the walls we could finally see, the clusters we could weigh in X-rays, and the far-off anchor of Shapley to make sense of the vector. And you needed to accept an uncomfortable idea. That absence could matter as much as presence. That the empty parts of the map might steer the currents as strongly as the crowded ones. While that was happening in Centaurus and Norma, a question gathered on the far side of the sky. If something pulls us, what's pushing from behind? That's where the next chapter begins. The map that moves, peculiar velocities and hidden currents. To understand the push, we had to get ruthless with motion. Start by taking the universe's expansion off the table. Every galaxy's redshift is a mix of two things: the Hubble flow that stretches space itself, and a smaller, messier term called the peculiar velocity, how the galaxy swims through that stretch. Subtract the expansion cleanly and the leftovers sketch the hidden currents. But get this wrong by a hair and you tilt the whole river. So the community went ladder by ladder, rung by rung. For spiral galaxies, the Tully-Fisher relation linked rotation speed to intrinsic brightness. Spin fast, shine bright. If you know how bright it should be, its observed brightness tells you the distance. For ellipticals, surface brightness fluctuations measured the pixel-to-pixel grain in a galaxy's light. Nearer galaxies look clumpier, farther ones smoother. When lucky, Type Ia supernovae offered standard candles that lit the way across deeper gulfs. Each method carried baggage. Selection affects skewed samples toward brighter, easier targets. Malmquist bias made you overcount luminous outliers at larger distances. And a zone of avoidance, dust shaved photons off every estimate, demanding extinction corrections that could quietly warp the results. Here, where the map got clever. Cross-matching became a survival tactic. HI surveys at 21 centimeters pulled in galaxies the optical catalogs missed. Near-infrared catalogs, less sensitive to dust, recalibrated distances in the dirtiest parts of the sky. X-rays flagged clusters you'd never see in starlight alone, their hot gas advertising deep wells of gravity. Then, with thousands of imperfect distance, velocity pairs, researchers built a velocity field, often with Bayesian or Wiener filter reconstructions that tame noise but keep the bones of the flow. The idea was simple. If nearby points all drift in the same direction after you strip out Hubble's expansion, something real is steering them. And a pattern formed. Velocity vectors lined up across swaths of the sky, not as random gusts but as a steady wind. The arrows near the Great Attractor region leaned that way, sure, but they didn't stop there. Streamlines, those imagined threads a leaf would follow, ran past the nominal basin around Norma and Centaurus and bent toward deeper structure. You could trace them like watershed lines on a topographic map. Where flows converged, you marked an attractor. Where they sheared, you drew the boundary between basins. What nobody knew at the time was how much the zone of avoidance had been sanding off the truth. Correct for extinction with infrared data, and some arrows pivoted a few degrees. Fold in HI detections behind the plane, and entire filaments snapped into place. A micro-story, A team reprocessed a patch near Vela with updated dust maps. The distance moduli shifted by tenths of a magnitude, small on paper. On the flow map, a cluster's peculiar velocity flipped sign, from slight approach to slight recession. That single flip nudged a chain of arrows and erased a phantom eddy that had anchored 3 years of conversation. Meanwhile, statistical landmines kept popping. Malmquist bias wanted to inflate distances for galaxies near your detection limit, faking an outward flow. Cuts meant to avoid it sometimes carved away the very structures you hoped to trace. The zone of avoidance turned crowded. HI line profiles blended, source confusion rose, and velocities of foreground gas smeared clean signals. So the field leaned on redundancy. Independent teams, different instruments, overlapping sky. If a flow feature survived 3 measurement methods, it earned its contour on the map. Then came the reveal that tightened the knot from pillar I when you stitched the best data together. The coherent stream pointed past the Great Attractor toward a deeper sink, aligning with reconstructions that would later define Laniakea's basin. Water doesn't stop at a midstream rapid. It glides through and heads for the valley. The flow lines trended toward the Shapley Concentration far downstream. The Great Attractor's gravity mattered locally, but the riverbed sloped on. Unknown to them, across the other side of the sky, underdensities were shaping the same currents. The reconstructions hinted at divergence zones, places where streams peeled away. At first, teams described lack of pull. Later, they realized it felt like a push. But that language fight belonged to the next act. For now, the lesson was blunt. Peculiar velocities aren't noise. They're the handwriting of structure on the expanding page of space. Clean the measurements, tame the biases, and the map starts moving. And once the map moves, it points, not at where we thought the journey ended, but at where the current insists we're going. The Dipole Repeller, the push we didn't expect. While the flow lines were threading past the Great Attractor toward Shapley, something else was carving the same pattern from behind. At first, it was a sentence people tossed into talks. There's less mass over here. But it didn't sound like a force. Then teams started rebuilding the map from motions alone, and the empty part of the sky stopped being a footnote. It became a driver. Here's the counterintuitive bit. Gravity only pulls. There's no anti-gravity in this story. But if one region is underdense, thinner in galaxies, thinner in dark matter, then surrounding mass exerts a stronger pull than the void side. Matter flows away from the low toward the high. Stand on a hill in a river and water will seem to push off you, even though gravity is pulling it downhill somewhere else. That's the repulsion in quotes, an effective push born from an absence. To make that idea more than a metaphor, you need to turn noisy velocity arrows into a 3-dimensional field. That's what the reconstructions did. Start with thousands of peculiar velocity measurements, galaxies and clusters with distances good enough to subtract Hubble's expansion. Feed them into a Bayesian or Wiener filter algorithm that assumes flows in the linear regime trace the gradient of a potential. Out comes a smoothed velocity field and, by inversion, a density field. Valleys where flows converge, hills where they diverge. In early 2017, Yehuda Hoffman, Daniel Pommard, R. Brent Tully, and Haleen Courtois pointed to a pattern that had been sitting inside those reconstructions. One side of the sky behaved like a classic attractor, Shapley's mass pulling streamlines in. The opposite side behaved like a hilltop. Flows peeled away from a vast, nearby underdensity. In their maps, the local group's motion and the direction of the cosmic microwave background dipole could be reproduced by a tug-of-war. Shapley on one end, a supervoid on the other. They called that emptiness the Dipole Repeller, no new force, just gravity acting on contrasts. The word did work it wasn't supposed to. Repeller sounded like a new force. The physics was old-fashioned gravity. In seminars, people fought over language. Was repeller an invitation to misunderstand? Or was it the clearest way to name a real feature of the flow, the divergence where galaxies accelerate away because there's simply less to hold them? Hoffman's team leaned into clarity. No new physics, no exotic fields. Just flows from empty to full, with the underdensity playing the role of a hill that water can't sit on. Meanwhile, something else clicked. The direction of that effective push roughly aligned with the local group's motion out to tens of thousands of kilometers per second in redshift space. That's technical speak for scale. The pattern held over a lot of cosmic real estate. If you plotted the bulk flow vectors as you stepped outward, they lined up against the repeller and toward the attractor like a compass needle trapped between two magnets, except the north wasn't a mass at all. It was a lack. A human beat from those weeks. A researcher walks into a colleague's office with a printout of the reconstructed streamlines. Two colored bundles, one curving toward Shapley, one bending away from the void. If this is right, they say, we've been explaining half our speed with only half the causes. The colleague stares, then asks the question the word repeller forces. Are we telling people gravity pushes now? The answer is patient. We're telling them emptiness lets other pulls win. Of course, the detection carried caveats. The predicted position of the repeller sat in a region thinly covered by redshift surveys. The void itself was hard to catalog with galaxies because it's defined by their absence. Algorithms that identify voids disagree about boundaries. Thresholds move edges around. But the velocity-based signal didn't care about seeing the void directly. It cared about coherent divergence in the flow, about where the arrows refused to point. Then came the payoff. Fold the repeller into the budget and the residuals shrink. The mismatch between the observed CMB dipole and the pull from known overdensities eases. The local shear, how quickly neighboring streamlines change direction, makes sense if you place a hill under one side of the map. Even skeptics who disliked the branding had to engage the balance sheet. Subtract the contribution of the underdensity and the numbers wobble. Add it, and they settle. There's a deeper lesson hiding in that accounting. When we talk about structure, our eyes go to clusters lit in X-rays, to bright filaments strung with star-forming knots. But the universe's scaffolding is a set of contrasts. Ridges and valleys need empty slopes between them. The dipole repeller is a reminder that those slopes aren't passive backdrops. They steer everything that flows nearby. Meanwhile, something else was stirring on much larger scales. A claim that there might be a current beyond even Shapley and any local void, a drift that ignored the map's edge. If pull explains our motion, what do we make of a rumor that says the whole pool is sliding in one direction? That's where the controversy walked in with a microphone. Dark flow, a claim too big to ignore. Here's the rumor that wouldn't sit down. What if everything, clusters hundreds of millions of light years apart, was drifting the same way, as if the whole pool had a tilt we couldn't see? Not a local nudge from Shapley, not the push of a nearby void, a current on scales the map didn't even cover. Alexander Kashlinsky and his collaborators had a way to check. Don't chase galaxies one by one. Listen for a whisper in the microwave afterglow. Hot gas in galaxy clusters scatters cosmic microwave background photons. If a cluster is moving relative to the CMB, it adds or subtracts a tiny bit of energy to those photons, the kinematic Sunyaev-Zeldovich effect. The signal is minuscule, buried under the CMB's own primordial ripples and a storm of foreground noise. But statistically, across hundreds of clusters, you can stack and filter. If clusters share a common motion, their KSZ fingerprints should line up into a dipole, slightly warmer on one side, slightly cooler on the other. Get this, they did the stack and claimed they saw it. A surprisingly coherent drift, several hundred up to roughly 1,000 kilometers per second, pointing roughly toward a patch between Centaurus and Vela. The press latched onto the phrase dark flow. It sounded like a hidden river. In talks, Kashlinsky's team pushed the implication. If the drift extended beyond where normal structure could cause it, gravity might be tugging from beyond our observable horizon. Maybe relics from inflation. Maybe something outside our cosmic patch. The idea turned heads because it punted past the guardrails. It dared you to think about what lay off the edge of the map. Meanwhile, desks filled with plots and skepticism. The KSZ effect is the quietest voice in a very loud room. You have to model cluster gas profiles, subtract foregrounds, choose masks to cut out contaminated CMB regions, filter angular scales, and hope your pipeline isn't inventing patterns. Teams lined up to replicate or refute. Some reanalyses found weaker hints. Others found nothing compelling. The word systematic started appearing in every paragraph. Did the filtering choices preferentially build a dipole? Were residual primary CMB anisotropies fooling the measurement? How robust were the cluster catalogs and their assumed profiles? Planck changed the tone. Full sky maps, higher sensitivity, better control of the microwave sky. When Planck teams applied their own methods, the case for a large-scale, horizon-busting bulk flow thinned to a thread. The claimed amplitude dropped. In many treatments, it vanished into the noise. A Planckiera null result wasn't just a quiet no. It was a statement that, within the instrument's reach and the models applied, there wasn't strong evidence for a universal drift beyond what lambdictum and known structures predict. Conference hallways got lively. Kashlinsky's group defended their pipeline, arguing that specific filters and cluster selections mattered, that Planck's null wasn't a generic death sentence for the effect. Others countered that if a phenomenon needs a particular set of choices to appear, you should get very suspicious. Rival analyses pointed at foreground leakage and profile mismatches. People drew arrows on whiteboards showing how a tiny bias at the filtering stage could leak a primordial CMB dipole back into the measurement and masquerade as KSZ. A micro story from one of those sessions. A postdoc stands at a poster with two panels. Left, their reconstruction with Kashlinsky's filter, there's the dipole. Right, the same data with an alternative filter that better suppresses primary CMB features. The dipole shrinks, then slips within error bars. A senior scientist leans in. So which panel is the universe? The postdoc smiles, tired. The one that survives more ways of being wrong. Here's where it gets important for our river. Even if the dark flow claim fades under Planck's scrutiny, the question it asked was useful. How do we tell local currents from global tilts? Are we mistaking poor subtraction for new physics? The field doubled down on cross-checks. Independent methods, peculiar velocities from distance ladders, density reconstructions from redshift surveys, weak lensing maps, had to line up. If a supposed large-scale flow didn't echo in other tracers, it stayed in the penalty box. While the headlines cooled, our neighborhood map only got sharper. The Dipole Repeller, Shapley tug-of-war, handled the observed local group motion in a way the data liked. Laniakea's flow lines, built from real peculiar velocities, drained past the Great Attractor toward deep structure without calling on super-horizon mysteries. You didn't need a cosmic tilt to explain why our arrows pointed where they did. You needed honest accounting, fewer blind spots, and respect for the quiet power of voids. Still, the lure of an edge-of-the-map influence didn't disappear. It moved into cleaner language, constraints. If there's any residual truly large-scale bulk flow, it has to sit under strict limits from Planck baryon acoustic oscillations and the CMB's tiny anisotropies. Theories that once strutted now tiptoe, labeled as speculative. In this game, humility pays rent. Back at the riverbank, you can feel the pivot. Dark flow was a dare. It forced better tools, tougher pipelines, and sharper questions. In the aftermath, what survived wasn't the rumor, it was the discipline. And that discipline points us back to the currents we can weigh, the pushes we can map, and the basin that quietly through the dust, cracking the zone of avoidance.